Okay, welcome to this week's GEOTOP-A seminar. Our speaker is Martina Scolamiero from KTH, assistant professor at KTH, and I had the pleasure of hosting as a postdoc several years ago. She's going to be speaking to us about stable and interpretable topological feature maps. Looking forward very much to your talk, Martina. Please go ahead.
Thank you very much, Catherine and other organizers, for the invitations. I'm really happy to be here and to share this news about these stable invariants we've been working on at KTH for some time now. So this is the plan of the talk. I will start by introducing these stable ranks, which are these features that we want to use for data analysis. And I will start with a very explicit example and show how this can be useful for noisy data. Then I will talk about an application of this invariant to understanding microglia morphologies, and this is in collaboration with Catherine, Lida Canari, Sandra Siegert's group, and some of us at KTH. I do this to show how stable ranks actually play in action in practice, how they can be used on real data and what they can tell us about the data. In the end, the other part of the talk will be a bit more general and will be about defining several stable ranks and the problem of how to choose among them, which are the specific features of these feature maps we build and how we can understand them. So let's get started. Most of you already know what persistence is, so I just have one slide about it. As you probably already know, in persistent homology, we start with some data, which could be a point cloud, set of points in high-dimensional space, or a geometric object with a function defined on it. Then we define a sequence of simplicial complexes which encode geometry in this data, and we want to study this sequence of geometric complexes through homology, which tells us about connectivity, holes, voids. So we transform this sequence of geometrical objects to a sequence of vector spaces and linear maps. This is what is called a persistence module. Starting from persistence modules, we can then represent this for data analysis either as a barcode, which is a multiset of intervals or points on the plane called persistence diagram, or in a functional way, and this is what I will focus on today through these stable rank constructions. Another common way to utilize this persistence information is through persistence diagrams, which are images which are created from the persistence diagram. So there are quite many ways to use this algebraic information of the persistence module. Each of them has advantages and disadvantages, and I will mainly focus on this idea of building functional summaries of the persistence module. So formally, a persistence module, the algebraic object we want to represent, is a functor from the real numbers considered with the standard order to vector spaces with coefficients in a field. And so for each index, we have a vector space, and then if we have one index which is smaller than the other, we have a linear map between these vector spaces. So we are thinking about sequences of vector spaces and linear maps between them. And everything is about comparing in this talk, so we want to compare persistence modules. And the way we compare such sequences of persistence of vector spaces and linear maps is pointwise. So for each v in our parameter space R, I have a linear map from fv to gv, and then I require commutativity. So if I go from fv to fw and then to gw, this has to be the same as going with my map pointwise from fv to gv and then with the transition map to gw. So we have sequences of vector spaces and linear maps, and we have morphisms between them to compare. And pointwise, which have these relations of commutativity, so compatible with the internal maps. Also, it is quite common to restrict the attention to the case where the vector spaces are finite dimensional and there are only finitely many changes in this sequence of these vector spaces. So this will be called Tame persistence modules, and this is the category we will focus on. So Tame persistence modules and morphisms between them. If one is more acquainted with commutative algebra, one can think of these as modules over the polynomial ring with one variable and morphisms between such modules. And the Tame ones are the ones that are finitely generated. I mention this because I'm actually interested in the number of generators, the minimal number of generators of a persistence module, which I call the rank. So we have seen earlier, and many of you already know this, that for modules over PID, so module of the polynomial ring in one variable, we have a decomposition into indecomposable. This is so-called the Barcode decomposition. If we think about this decomposition, the rank of a persistence module is just the number of bars in this Barcode decomposition, which we have seen graphically before with these intervals. So, as an algebraic invariant for persistence module, one can consider the rank, number of bars in the Barcode decomposition. But it is very discrete. It doesn't seem perfect for data analysis, where there can be some errors, some perturbations in the data, so small bars can appear, and this invariant can change drastically. So the idea is not to consider this very discrete invariant just counting the number of bars in the barcode, but define a function which considers the rank of my persistence module within metric neighborhoods. So the first ingredient here is to define a distance between persistence modules. How do I compare persistence modules? I have to define a distance between them. Once I have my distance, I can say, okay, I look at the rank of my persistence module, and then I look at a metric neighborhood. Okay, in this metric neighborhood, which is the minimum rank I can achieve? How many bars can I take out and still be close to my persistence module? Doing this for various parameters, various values of a parameter, then obtain a function, which is what we call the stable rank. So I look at metric neighborhoods of my persistence module with respect to a given metric and the minimum rank in such metric neighborhoods. Okay, so this creates a function, which is non-increasing by construction, and one of the properties is that this function is actually stable with respect to the original distance we had between the persistence modules. How do I phrase stability? I usually think about stability in a metric way, so I think about Lipschitz stability. I have a distance between persistence modules, I have a distance between functions. I want to say that the map going between these two metric spaces is Lipschitz. So the distance between persistence modules is the one I use to build these neighborhoods. The distance I would like to use between my function is this so-called interleaving distance. The definition is as follows, but it's better explained with a picture, actually. So we say that two functions, f and g, are epsilon interleaved if f of v is greater or equal than gv plus epsilon. So if it's below, but I move by epsilon, it reaches the same level. And g of v is greater or equal than f of v plus epsilon. So the same happens for g. If it's below, but I move, then it goes above. This tells us that up to approximation, the functions go decrease together, and this maximum epsilon for which the functions are interleaved is this distance that is highlighted here by this arrow. It's the maximum value on the parameter space I have to move to reach the other function once I'm below. So this is a distance to see how these functions decrease and make sure that they do it one close to the other. This is the interleaving distance and the way I can compare functions, which are non-increasing, actually decreasing. So here is the stability I was mentioning before. The interleaving distance between stable ranks of two persistence modules, f and g, is smaller or equal than the original distance between my persistence modules, f and g. So it's 1 Lipschitz. It's stable, and it's very easy to show stability because it's by construction. Since we have triangular inequality for this distance d between my modules f and g, this triangular inequality implies that in this minimization process, I obtain this inequality. The obtained functions are interleaved. But we also have stability results for other types of distances between stable ranks, as for example, integral distance. In this case, I will have to introduce a constant depending on the maximum value of the stable ranks in the inequality. Anyhow, from a very discrete information about my persistence module, number of bars, I obtained a function that tells us about number of bars up to approximation, and this is an invariant which is stable with respect to the original distance. Okay, so here is my first example. Well, what I said is a bit general. It's just a framework to build things, and I actually compute and define such feature functions. The simplest thing I can think of is the following. We call it standard distance. I will first introduce the distance to compare persistence module and then the induced stable rank. So I start by saying what I think is small. And for me, something is small if all the bars are short. So I say that something is epsilon small if for each x in one of these vector spaces, x is in the kernel of the map from fv to fv plus epsilon. So these maps that move on the parameter space by epsilon, they are 0. A generator cannot move more than epsilon in the parameter space, which at the level of barcodes tells me that all the bars are shorter than epsilon. This is what I claim is small. And then we will see later there are some conditions that these sets of small objects have to satisfy in order to define distances. But if these conditions are satisfied, then I can define a distance based on what I think is small, and the distance is defined as follows. So I have two modules, f and g, and I say that they will be epsilon close with respect to this notion of smallness if there exists a third object, a witness, and maps to f and g such that the kernel and co-kernels of these maps are small with respect to various constants, and these constants sum up to at most epsilon. So this is to say that maybe there's not directly a map from f to g or g to f, but I can find a common persistence module interpolating between them, and this is close to f and close to g. So f and g must be close. This is the idea. The distance is defined again as the infimum among all epsilons such that f and g are close. I should mention that it doesn't seem so. As I said, it maybe doesn't sound exactly the same, but this is very related to interleaving distance between persistence modules. It's actually equivalent up to some constants. So we can think of this as trying to match maybe two barcodes or two persistence diagrams and looking at the maximum error that we commit by considering this matching. It's about maximum error because I'm considering maximum length of bars. Okay, and with this notion of what is small and associated distance between persistence modules, I can define my stable rank. And how will it look? It's a bar count. First of all, I can notice that in this case, I don't have to look through these big neighborhoods which are infinite and in some cases actually very complicated, because I could simply look at submodules of my given functor and just take away bars. Or I can actually quite easily prove that stable rank, so this functional summary of the persistence module, is additive for this specific type of distance. So the stable rank of f, written as direct sum of bars, is the sum of their stable ranks. Stable rank of a bar is just 1 or 0, because this is just, a bar is just k in a part of the interval and 0 otherwise. So stable rank of a bar is 1 and 0. It goes to 0 when I hit the length of the bar. So when I take the sum of all these indicator functions about the different bars in the barcode, I'm just counting how many bars I have of a given length. So the stable rank at step t is the number of bars whose length, so def minus birth, is greater than t. So it became very explicit. I had a very formal description, but in this case, which is the easiest one, is the most concrete one, it became very explicit. The summary, the functional summary I take of my persistence module with this given barcode is counting how many bars I have, and then for each t, I count how many bars I have of length at least t. Seems quite simple, but it's just an example of a more formal framework. And although it seems simple, it can be actually very useful in an application which I will now tell you about. And the reason is that these stable ranks, since they are functional summaries, they are very simple functions, decreasing functions, they are easy to compare. We can take distances between them, we can take averages between them, we can consider integral distance between them, and the Hilbert space associated to this. So we can actually look at angles between these functions, and rather than computing the distances, we can compute angles between these functions as a way to map the data. And so Jens Ageberg came up with this idea of building the stable rank kernel, which is a kernel which to two persistence modules associates the integral of the scalar product of these two functions, the stable ranks of x and y. Stable rank kernels are very useful because they allow us to input this data representation of the stable rank in machine learning methods that are so-called kernel-based. So we look at scalar products of data representation as this kernel between the associated stable ranks. And here is how this was used in practice in a project that was about understanding morphologies of trees. It all started with the topological morphology descriptor, which was introduced by Lida Canari at Blue Brain Project. Topological morphology descriptor is a method to extract persistence information, shape information of a tree in the form of a barcode or a persistence diagram. So the input is a rooted tree. We have a geometrical tree in R with a specified point called the root. And then we have nodes, which are either branching points or leaves and edges. We are also interested of having as an input a function from the nodes of the tree to real numbers. This function could be, for example, distance to the root, which would be represented by the soma if one looks at neuronal trees, or one can look at path distance, or various other metrics that are interesting for the problem at hand. So we start with a geometric tree, consider the combinatorial object associated to that and a function of this, and the output of the algorithm is a persistence barcode, which tells us how branches appear and merge at these different distances, at different values of the function f to the reference point, the sum. So here is an example. The way the algorithm is actually thought about is by considering two orders. One order is the one given by the function. Here, for example, distance to the soma, distance to the root. And the other order, which is considered, is the parent-child relation. So the original algorithm is defined by iteratively going through all the nodes in the graph, in the tree, and considering, starting from leaves, for each leaf, which are its parents, and among its while we look at its parent, we look at all the children. Each children will be another node. Each node is associated to the bar. The bar corresponding to the furthest child continues in the process, while the bar corresponding to leaves which are closer with respect to this function f, so have smaller value of this function f, are killed. So terminate at the value of the function for the parent. So with this parent-child interaction of parent-child relation, we go through the tree and we take into account the value of the function f. In some cases, where we don't have ingoing branches, as this one here, one can actually think of this, for those of you who are into persistence, sub-level set persistence of a function defined on the node of the tree. So one starts from the outermost part of the tree, look which leaves appear. We start with H here. We start from TMDs from left to right, at least at this point. So we start with H. We go in one step, find G, another leaf. Then when we reach J, G terminates, H continues because H was further on, and so we continue. So it's a sub-level set persistence on a function defined on the nodes. In this small example, here is the barcode, and here is the associated persistence diagram. It's worth noticing that the computational complexity of this algorithm is linear in the number of nodes. So this is absolutely feasible on real data. And it's actually very interesting to see, for example, here, as neurons of different species have very different representations through the TMD algorithm. So here you can see neurons that come from cat, dragonfly, fruit fly, mouse, and rat, and corresponding samples, corresponding representatives of the associated barcodes, persistence diagrams, and persistence images, which are obtained through convolving the persistence diagram with Gaussians. So one property which is pretty interesting in this case is the fact that this algorithm looks at the distributions of bars in space and represents them as different clusters in space. So we can see, for example, here in the second and last that there are two clusters corresponding to the two main parts where the branching happens in the tree. So the part where I was mainly involved in this project while I was at EPFL was looking at the stability of this algorithm, and it was interesting to see that the TMD is actually stable with respect to perturbations, which we expect when sampling the tree associated to a morphology. And these perturbations are omission of a short branch or the exact position of the branching points. So in the paper by Lida Canari and others, we were able to show that it's stable with respect to these perturbations. One aspect that was not considered so much at the time, but came more into play into the second project I will be discussing now, is actually intrinsic variability in the data. At the time, we were especially focusing on understanding stability with respect to perturbations in the data, and looking at more simple or complicated classification problems, but a huge variability in the data came up when we started looking at microglia morphologies as extracted and analyzed by Sandra Siegert's lab at IST. So microglia are immune cells in the brain, and I'm not an expert in microglia, but from my understanding, the populations of microglia are not homogeneous at all, because these cells are very dynamic. So they change in time, they change across condition, and in the imaging, they can be very, very different. So here is a figure from this project we did together with Sandra Siegert, Catherine S., Lida Canari, and the corresponding groups. So here, one of the goals of the project was to understand if microglia coming from different brain regions were structurally different. So these are brain regions in mouse. And the pipeline introduced by Lida Canari could actually be performed on trees representing microglia. So this was possible, and starting from a tracing of the microglia, it is possible to define a rooted tree, as the one I showed before, apply TMD, topological morphology descriptor, and construct a barcode decomposition of the associated persistence module, persistence diagram, and then persistence image by considering Gaussian kernels. Here, in this case, one can also look at average persistence images. So if we fix some groups of microglia, one can look at the average within each group. But the problem was that since there is this large variability in the data, single microglia morphology representations were very different within each group, and we needed something in between, as the average between the average per group and the single representation of a microglia. We needed something which still represented the variability of the data, but trying to avoid some of the noise. So Ryan Curbero proposed a bootstrapping method, and the idea is to start from a population and of size n, and choose a number, sample microglia representations in the forms, for example, of persistence diagram, the number that has been chosen, and perform averages of such bootstrap samples. So, for example, if we have n as total population size, and then we subsample x cells from the population, take averages of them, and then as a bootstrapped population, we consider these averages of x cells chosen among the n within each condition we want to compare. So this actually turned out to be able to separate microglia representations through TMD and persistence images from different parts of the brain. So if we sample, for example, microglia from cerebellum, they are very different from microglia coming from other brain regions, and some brain regions are closer to each other, some are more separate, but it was possible to see a clear distinction. It was possible to see that the persistence images associated to the TMD of the microglia managed to encode these structural differences between microglia coming from brain regions through bootstrapped samples. We also tried with the stable ranks with this type of distance that I have been talking about, so this standard distance between persistence modules and associated standard stable rank. So this creates a functional summary of the length of the bars in a barcode decomposition. And if we do the UMAP of this representation of the data, we see a pattern which is very similar to the one you could see from the persistence images. So if this is the one with persistence images, and you don't look at the exact shape in the plane, but the grouping, how things are close and how they merge, you can notice that this is reflected also by the stable rank analysis. And so this just tells us that in this case, the persistence of the bars in the barcode decomposition of this representation of the morphology was an essential feature to identify region-specific characteristics of these cells. And we also wanted to assess the effect of bootstrapping. So we have averaged per group, per brain region, we have averaged a certain number. And we could do this with the stable rank kernel, so we can perform pairwise classification and look at the accuracy. And here you can see the various brain regions and the accuracy with respect to pairwise classification with support vector machine and the stable rank kernel. And although we can see that there's lower accuracy with no bootstrapping than with when we average a lot, so with large values of bootstrapping, we can also notice, and this was quite interesting to see, that the patterns remain the same with bootstrapping and not. So when the accuracy is high, we can see that it's high also with bootstrapping, and when it's low, it's similarly low with the bootstrapping. Although when we obtain sample size 50, then actually the accuracies were all very good. But in general, the idea was to assess how this bootstrapping procedure was homogenizing the data, and if the patterns that we could see after bootstrapping were already there, although less strong on the original data. So our small contribution with the stable rank in this project was to understand which parts of persistence were important for the classification problem, so highlight some properties of the persistence diagram which were important for the classification problem, and understand with a classification rather than a dimensionality reduction in different conditions how this process actually changes. Maybe this is a good time for the 20 minutes break, or is it too late already?
No, it's a good point. Any questions for Martina? It seems not. I think you can go ahead, Martina.
Okay. So up to now, I have presented an example of stable rank for a specific notion of what I think is small. And the idea is that now we would like to generalize this and find other types of notions of smallness. And to be able to define a metric from this notion of smallness, the axioms, the compatibility axioms that this epsilon small must satisfy is the following. So this is a bit axiomatic, but it's the idea is it's just a way to check if what I declare is epsilon small is good enough to define a metric to compare persistence modules. So we want to say what is small and what is epsilon small, and this is the set S epsilon, which contains all modules that are epsilon small. And I want the module 0 to be as small as I want. So this is the persistence module, which is everywhere 0. And then I want that if tau is smaller than epsilon, then if something is tau small, it's also epsilon small. And this you can see in this representation here. So if I have my little matrioskas and I order them by size, if one is smaller than the other, it has to fit into the bigger one. And then I have this requirement about sub-objects, kernels, and short exact sequence. So if we have a persistence module and one which is contained in it, so there's a monomorphism, then if G is epsilon small, then also the one that is contained in it should be epsilon small. Same for quotients. So if G is small, and then I consider a quotient of it, this also should be even smaller. And then if I have a short exact sequence, I intuitively think that the middle one is composed, built up from F and H. And so if F is epsilon small and H is tau small, then G must be epsilon plus tau small. These are requirements which look a bit formal, but actually they are good conditions to define a metric in the way that I said before. And now for the rest of the talk, I will discuss two ways of what can be thought as small, so of noise systems, and what are the associated stable ranks. The first one is the one induced by contours. A contour is an action of the additive monoid 0 infinity on the ordered real line, 0 infinity. So it has to follow these properties that if I act by 0 on A, I stay there, I stay on A. If I act first by epsilon and then by tau, it's the same as acting by epsilon plus tau. And then it's order preserving in both components. Each contour defines a noise system, so a notion of what is small. And we say that a Tame persistence module is epsilon small with respect to a given contour if when I go from degree V to degree T of V epsilon, then each element goes to 0. So these maps have to be 0. This looks very much what I had shown before, but before I showed the case where CV epsilon is V plus epsilon. So the idea is that I don't move from V to V plus epsilon on the line of parameters, but I move from V to the action of epsilon on V by the contour C. So how much the contour moves V by epsilon. And so contours can be thought as a way of how to flow on the parameter line, where to speed up and where to go slowly according to where I am on the parameter line. And this is particularly true if I think about a type of contours which are defined by functions. These contours are regular, which means that they are monomorphisms in both variables. This is a bit of a technical requirement, but it's really useful in what follows. So these contours I'm thinking about are defined by densities. So for each integrable function f, I say that I act by epsilon on A, and this is how much I have to go on the parameter line to span an area of epsilon under the curve. So how much do I have to move to span an area of epsilon under the curve? This is the contour df A epsilon, parameterized by f. So this is not just one type of contour. We have one for each measurable function. These are many. And it's interesting that for these regular contours, we can define a notion of lifespan, which is a generalization of length. When we consider the contour which to A and epsilon associates A plus epsilon, the lifespan is basically the length. So it's the depth minus the birth of a bar. In general, the lifespan of a bar is how much I have to act on the birth to reach the depth for a given contour. So this is a way, as I said before, to weight different parts of the parameter space differently. If I have a bar in the beginning of the parameter space and I consider this function f, the lifespan of the bar b1, d1 will be L1, this big area. If I have a bar which is towards the end of the parameter space, its lifetime will be L2, which is much smaller. So although they look the same, the depth minus birth, if I look at not the length but the lifespan with respect to the contour defined by this function f, which emphasizes the first part, it will take much longer to go from B1 to D1 than to go from B2 to D2. I want to emphasize different parts of the parameter space. And then, very different from this is the notion of p-norm of a persistence module. And this was introduced by Kate Turner and Primož Škraba recently. Given a persistence module, they define the p-norm of the persistence module as the sum of the p-power of def minus birth of each bar, and then everything to the 1 over p. And for p equals infinity, it's just the maximum length of the bars. So it is already shown in the paper that if one looks at all the persistence modules which have p-norm smaller or equal than epsilon, this follows the axioms of a noise systems, the ones I showed before. Although this is not explicitly stated in terms of noise systems, and one of the proofs, which is the hardest one we're working on recently, that the middle term of a short exact sequence is a noise of size, the sum of the noise of the extremes. Well, the proof of this for them depends on the fact that actually these norms define a distance which follows triangular inequality, and we don't want to use this here. We want to prove that this norm follows some axioms which then will define a distance. So we don't know a priori that it will define a distance. We want to prove it algebraically. We don't want to relate this norm to a distance and then use triangular inequality on that distance to prove this. We want to first prove this and then say that therefore it will define a distance. But anyway, it was very interesting for us to see that this type of measure of size of a persistence module, which is defined the p-norm, actually follows the axioms of a noise system. And it was interesting because these p-norms are noise systems which are very different to the contour-based noise systems, but they can be integrated. So this is what we found the most interesting, that it's quite trivial to modify this definition and not consider def minus birth as the length of the bar, but rather lifetime with respect to a given contour. So by modifying the definition in this way, we can define a norm of persistence modules which considers both p-Wasserstein, the way I aggregate length of each bar, and the contour, which is a way in which I flow over the parameter space. And then we have a very similar proof to the algebraic proof. With no contour, we can prove that also this new definition defines a noise system. When I consider actually regular contour as for the ones defined by a function. So I said that it's very different, the p-Wasserstein, from the contour one, and this is because the ones defined by contour are closed under direct sums, which means that if x and y are noise of size epsilon, also their direct sum is noise of size epsilon. So contour type noises follow this. Instead, p-norm noise don't do that at all. So we don't, and this is because we don't look at the maximum size of a bar. We aggregate all sizes with p-norm, with p-norm in Euclidean space. So we are aggregating all the information, not looking at the maximum length, so when p is different from infinity. So they are noise systems of different nature. And here is a simple schematization of various noise systems that I came across working on this topic over the years. So among them we have p-norm and p-norm with contour, or this standard noise system which I showed before, which is an example of simple noise systems, which are the ones defined by contours. Exactly as I said before, a noise system defines a metric, so this is exactly the same construction as before, but before we were thinking about that specific noise system, the one where we look at the maximum length of the bar. So I will not repeat this, but the idea is that once you have a notion of what is small, this is I get, and it follows the axioms of noise systems, then we can define a distance between persistence module from that. And if we change a little bit the definition we had above, so rather than taking the sum of the contributions, we take the p-norm of their contributions and the noise system given by the p-norm, defined by Turner and Scraba, we obtain exactly what they had defined as algebraic p-Wasserstein distance. So this construction is the same as what they presented in the paper. And in this paper, they also present an equivalence between this p-Wasserstein distance and the Wasserstein distance between persistence diagrams. So this is how they know that that is actually a distance that follows triangular inequality. So it's nice for us to know that this notion of Wasserstein distance between persistence modules is in the framework of noise systems and how we constructed metrics from that. As I said, we have notions of what is small and induced metrics, and we are particularly interested in family of metrics. For example, if we have this parameter p of the p-Wasserstein and we consider all these metrics, then one might ask, okay, which is the best p for a given data set? It's not always the case that p equals 1 or p equals infinity is the best. Maybe it's something in between. It depends on what is signal and what is noise. And similarly for contour type distances, which part of the parameter space should I emphasize intuitively? And if I put them together, how should I learn all of these parameters? The situation gets a bit complicated, but interesting at the same time. I said that we were particularly interested in this notion of size of a module given by the p-norm and the introduction of contour to use lifespans. And we use distances to create invariants. So we use distances to create the stable ranks in this work. So is it easy to compute the stable rank starting from the p-norm contour Wasserstein norm? It turned out to be not so easy to prove, but a very easy formula in the end. And the main ingredients for the algorithm to compute the stable rank in this case were the following. So first, we could reduce to mono-epi spans. So we could see that if there is a module minimizing the distance, minimizing the rank in a given neighborhood, there exists another one, which is connected to the first one via mono-epi span, and it has the same or less number of bars, so same or less rank, and it is in the same neighborhood. So we can reduce to this type of spans. The second observation, which was crucial here and to prove the last axiom of noise system, was that the so-called bar-to-bar monomorphisms are the ones which have smaller kernel in terms of this norm. What is a bar-to-bar monomorphism? If we have a map between barcodes, we have a bar that could map to several other bars of the other barcode. We have some conditions of how these bars should be arranged, so the top one should be on the right of the second one, but we don't know that it just has to map to one bar downstairs. It could map to many. It's more complicated when it maps to many than if it maps to just one bar, because the morphism is not a direct sum of bar-to-bar morphisms. But we could prove that these bar-to-bar ones, which are the easier ones, are the one with a smallest norm. So we could actually reduce the search in these neighborhoods to mono-epi and bar-to-bar morphisms. With these two things in mind, we managed to prove the formula for the stable rank for the p-Wasserstein contour type distance. And we saw that the stable rank is, of course, a decreasing function every time it decreases by 1. So it's a function that has all the values from the rank to the module up to 0. if we assume no infinite bars, which we would like to assume. And where does it go down? One step each time. Well, at these discontinuity points here, which are a constant times p-norm of the lifetimes of the shortest I bars. So we have to compute lifetimes of bars and their p-norm. Here, for simplicity, we can think that the barcode is ordered based on the lifetimes of the bars. So we have sum from I to k of BIDI, where L1, Lk, the lifetimes of these bars are ordered. And to understand at step I the value of this function, well, we just have to take the p-norm in Euclidean space of these numbers, length of the bars, times a constant. This constant is related to how we map bars to 0. So in p-Wasserstein distance, to map a bar to 0, you have to send it to half of the bar and then to 0. You don't map it directly to 0. This is the minimum cost one has to pay to map a bar to 0. So these table ranks are completely defined by these points ti of this discontinuity, which just depend on the lifetimes of the bars. And now a little bit about the intuition. How am I doing on time? Okay, I'll speed up so I finish in 5 minutes, if this is okay. Okay, this is an artificial data set. So we have two classes of images, which was artificially created by us, and it's part of work in progress with Andrea Guidolin, Isaac Ren, and Ian Sageberg. We have two distributions, one distribution for high-intensity pixels, which are the green ones, and one distribution for low-intensity pixels. We create two families, one in which the distributions for high-intensity pixels are different, and this is this example here. So this is a sample barcode from class B, sample barcode from class A. It's high-intensity pixels that change, and a sub-level set filtration on the intensity of the pixels, so it's long bars which are different between these two distributions. The low-intensity pixels instead follow the same distribution in both classes. Okay, so we compute p-Wasserstein distance, and intuitively, what should one think? So it's long bars playing a role by design in distinguishing these two classes. Well, one should think that it's a large P that should be better to distinguish these two classes in this case, because it's long bars that matter to distinguish. And if we in fact consider these stable ranks with P equal 1 and do hierarchical clustering, we see that the classes are quite mixed, but with P equals infinity, we can recognize the classes very well. Similarly, if I consider same distribution for high-intensity pixels and different distribution for low-intensity pixels, I expect short bars to play a role in distinguishing the two classes. And indeed, if we compute stable ranks with P equal 1, we get very good separation, and stable ranks with high P, the classes are less distinct. And one can actually organize the data so that this is less structured. So the intuition is that if short bars play a role in distinguishing between classes, one should choose a small p. If it's longer bars, one should choose larger values of p. And here it's just one parameter, so there's not much learning to do with just one parameter. One could just try a grid search and see which p is best for the problem at hand. But in this last example, I will talk about, we consider the interaction of P and of a contour. So the data set is a classical one in TDA, and it comes from the study of brain artery trees. And this was part of the work of Paul Benedich and co-authors. And they showed in this paper that topological properties of these 3D reconstructions, topological properties encoded as H0 sublevel set persistence with respect to the Z coordinate in space, correlates with the age of individuals. And so we divided the data into parts, A and B, which had similar number of data points. Class A, age smaller than 45, class B, age greater or equal than 45. And we wanted to understand if with stable ranks we could recapitulate this correlation between the topology and age, and in particular be able to distinguish the two classes. And we were also interested in understanding which parameter P and which contour C would be best to do this separation. So the idea is to set up a metric learning problem, and with the outcome of the metric learning problem, just use a classifier, which was k nearest neighbors. In the metric learning problem, we used a simple function between distances of stable ranks. So we used interleaving distance of stable ranks, and the objective function wants to have, of course, elements of the same class with high value and elements of different classes with low value. So we want to incentivate elements with the same class to have a small distance. And as families of contours, we chose Gaussian mixture with two Gaussians. So this is the means and the standard deviation of the two Gaussians. We don't have a complete understanding of the optimization problem actually, but we found that it was quite stable through runs, and we could see that this is an example over 25,000 iterations. So the loss function decreases, the parameters stabilize, so the parameter P stabilizes somewhere around 1, and then the averages and the standard deviation of the two Gaussians also tend to stabilize to various values. And here you can see how the density changes over the optimization problem. So the parameter P we go to is around 1, and this is actually coherent with the findings of Bendik et al., saying that short bars mattered in that case. And the contour that we found the best was this one with a darker color. Here you can find the contour and the corresponding part of the parameter space highlighted on the barcode. So most of the cases, this optimization problem converges, and with the obtained contour NP, we can perform a classification. And it was interesting to see that the best classification happens when one optimizes both the contour and the P together. So actually the interaction of the parameters is giving the best result. So overall, I hope to told you that table ranks can be used in practice on real data, and we are interested in parameterized families of stable ranks, which we can search, and we are also interested in optimizing within these families and understanding how these optimization procedures work and what the optimized stable rank can tell us about the data. Thank you for your attention.
Thank you very much, Martina. Thank you for a lovely talk, very interesting and wide-ranging. Are there any questions from the audience? Please just speak up if you have a question or a comment.
Hi, Martina. Could I ask a question?
Yes, sure.
Yeah, so I'm a little bit confused by the clustering results you showed, the hierarchical clustering results you showed early. If you could go back to the slides where the first appeared. Yes, so I think the first time, yes. So I'm actually really curious why, because the two examples you show, maybe I missed some crucial information. The two images you show that has a square, yeah, this picture here. I mean, somehow these two images, you could imagine there's two examples where those two images is just like a 90-degree rotation or 100-degree rotation. of each other, which in my mind, if I'm computing some sort of persistence, their persistent diagram should be very similar. Did I miss some crucial information where the direction is very important? The actual position of this is important in your classification?
No, so the position is not important. It's the pixel intensity that values. So this is a bit darker and this is lighter. So this turns out in different length of the persistent feature. Here the persistent feature is shorter than here.
I see. Okay, so it's not the position but intensity that is differentiating those two. Okay, all right. Thanks for clarifying.
No problem. This could actually be considered as pixel all over the place. It was for visual clarity that they were clustered all together. So the rotation would give something very close to this, at least in the same class.
Okay. Yeah, thanks.
Yeah.
Thanks for the clarifying question, Bei. Any other questions? Maybe a question for me. So, do you have any real data to which you're thinking about applying these techniques?
Yes. So, good point. I think the microglia data could be a good example. So we have previously tried with different density-based contour on microglia, and this was not achieving completely different results. So it was not density-based contours which performed much better than the standard one. But maybe the additional p-parameter could help because it shifts the focus from just considering the longest components to all the components in the barcode. So maybe combination of contour and p-parameter could be interesting in the tree data. So I think this tree data is quite interesting because it's relatively simple with respect to our applications to go back to the original data. So to map back to properties of the original data. Properties of the barcode, because when I say about interpretable, for us it's interpretable on the barcode, not on the real data. So it's interesting to have constructions where you can actually go back from the barcode to the data and see what that means.
Yeah, which is relatively easy with the TMD, indeed.
Yes, exactly. But much more difficult for other types of constructions of persistence.
Yeah, indeed. Okay. Are there any other questions in the audience? Okay. Well, if not, then thank you very much, Martina, for a lovely presentation. And thank you, everyone, for attending today's talk. And I wish you a very nice weekend. For those of us in Europe, it's the end of the week, so we can... and look forward to the next episode in this series of seminars. Thank you.
Thank you.